Many facility operators rely on a single management dashboard, displaying a green status to determine their plant's health. A screen showing perfect uptime looks reassuring in a boardroom, but beneath that monitor sits a dense, highly pressurized, and vibrating mechanical reality. The heat load in a data center does not care about a rating objective. It responds strictly to the immediate physical capacity of the cooling loop. If the underlying hardware fails during a thermal event, a software readout claiming 100% uptime offers zero physical protection. Keeping a facility online requires a strict engineering pipeline known as the digital thread. This pipeline converts abstract regulatory requirements into traceable design, physical testing, and operational evidence. A facility's resilience remains a dangerous fiction until every design requirement is mathematically and physically proven in the field. Looking at this diagram of the governance stack, the absolute foundation is the bottom red tier. These are adopted statutory laws, local building permits, and authority having jurisdiction, or AHJ, conditions. They are mandatory and strictly non-waivable. Directly above that legal baseline, we find the middle layer of consensus guidelines and sector standards, like ASHRAE. At the very top sit the owner-specific service level agreements and independent tier rating objectives. A voluntary standard, a sustainability rating, or an owner waiver can never legally displace an adopted AHJ safety condition. The law always wins. Operators frequently prioritize an owner's SLA over local municipal code, assuming the higher standard supersedes the baseline. Doing so creates an immediate legal liability and builds hidden fault lines waiting to cascade through the system during a critical failure. This schematic highlights the specific operational and inspection boundaries across a chilled water plant and server floor. Cascading mechanical failures rarely happen in the center of an isolated asset. They occur at the seams between independent systems, requiring strict interface ownership to prevent a system collapse. The mechanical boundary defines specific supply and return conditions, establishing precise isolation points and pressure classes for every pipe and drain. The electrical interface dictates transitions between normal and standby power, enforcing the exact load shed sequence. The controls boundary relies on a rigid separation of duties. The building management system merely coordinates approved operating modes. The local hardware controllers retain absolute final safety authority over the physical asset. When sizing these systems, engineers separate design margin from physical redundancy. Margins account for calculation uncertainty and extreme weather conditions. Redundancy determines exactly how an asset can be isolated for service without losing the required thermal duty. Every single interface requires an explicit owner, a testable acceptance criterion, and a precise restoration rule to verify these boundaries hold under extreme pressure. This graphic shows the installed system verification loop. It is a strict pipeline designed to bridge the gap between abstract design codes and active physical operations. It forces every engineering decision through a controlled sequence of verification. A requirement is never closed just because it is drawn on a blueprint. Closure requires an approved equipment submittal, physical verification of the exact asset tag in the field, calibrated measurement tools, and rigorous pass or fail exception decisions. This traceability framework dictates the validity of a facility's most publicized efficiency metrics, like power usage effectiveness and water usage effectiveness. The mathematics of these metrics are entirely irrelevant if the physical placement of the meters remains undefined. Watch what happens to the output on this floor plan if the defined boundary of the utility meter expands and contracts to include or exclude specific power losses. The resulting PUE calculation wildly fluctuates, even though the underlying IT load has not changed at all. You cannot evaluate performance accurately without verifying the physical source of the data. Never compare metrics across sites unless the energy source, IT meter location, and water scope are perfectly aligned. A metric without a verified boundary is just marketing. This timeline illustrates the formal progression of commissioning. Levels 1 through 3 are entirely component-focused. Teams conduct factory design reviews, verify installation tags, and execute point-to-point electrical checks to ensure sensors and power lines are properly terminated. The critical transition occurs at level 4. During the heat load test, operators apply representative electrical loads directly to the server floor and reconcile that generated load with the measured cooling duty of the plant. At level 5, the integrated systems test, Operators intentionally initiate controlled failures. They verify the automatic response of the mechanical loop, track residual capacity limits, and confirm that temperature excursions stay within the declared operating envelope. Surviving the failure requires a strict restoration proof. Operators must return the system back online one controlled step at a time, confirm standby availability, clear all manual overrides, and formally sign off on the restoration record. The true purpose of this entire commissioning sequence is not to verify that a chiller runs on a sunny day. It exists to definitively prove the system's ability to survive and recover from cascading failure under maximum IT stress. The ultimate stress test for this governance framework occurs during a controlled cutover. Executing high-risk mechanical changes on a live, active data center without dropping the IT load is a zero-tolerance maneuver. The days leading up to the change require strict pre-staging. Teams secure method of procedure approvals, issue facility-wide change freezes, and physically verify backup paths. Then comes 0 hour. The plant transitions from a protected pre-staged environment to active integration. Live data suddenly hits the modified mechanical loop. At this exact moment, strict rollback triggers dictate survival. Any loss of residual capacity, any unexpected alarm, or a single gap in test evidence mandates an immediate halt and a full reversion to the last proven state. Planned cuts test an engineering team's discipline, but those strict non-negotiable rollback triggers are what guarantee the facility's survival when operating limits are breached. In a total failure scenario, the prime directive takes over. Life safety and thermal stabilization dictate that operators rely entirely on local hardwired safeties, bypassing high-level software optimization loops to protect the facility. This flowchart maps the discrepancy workflow. When the digital thread breaks, first isolate the asset and freeze data trends to preserve the as-found state. Once stabilized, verify calibration, authorize a management of change order, and execute a retest to establish a new baseline. Reacting to a mechanical anomaly without first freezing the data logs permanently corrupts the site's compliance baseline. True operational compliance is an active, continuous, and uncompromising alignment between physical behavior, control logic, and documented evidence.